So looking at chapter 9, and this is the chapter on constant acceleration. I'm going to do a few introductory remarks, so if you want to dive straight into displacement time graphs, perhaps fast forward a little bit. Before we get into constant acceleration, we know speed equals distance over time, okay? Now that equation is if we have a constant speed, we've got speed equals distance over time, all right? And that comes back in here. Instead of a constant speed, we could think of it as an average speed if you want, or an average velocity is the displacement from starting time divided by the time taken, or the average speed is the total distance traveled divided by the time taken, okay? So if we've got a constant speed, practically in the real world, we're never really going to have a constant speed. Even if you're trying to drive a car at exactly a constant speed, it's very difficult to not make it fluctuate up and down a little bit. But we can think of the average speed as the total distance divided by the time taken. Now, this chapter is one step on from that. That's if we've got average speed, and we're going to deal with that's if we've got constant speed. We're now going to deal with constant acceleration. And because that's, acceleration is a more complicated measurement than speed, describing constant acceleration situations is going to be mathematically a bit more complicated. We're going to deal with that. We're going to deal with it in two halves. We're going to deal with displacement time graphs and velocity time graphs to start with, and then we're going to deal with what some people call the Suvat equations, or the constant acceleration formulae, and there are 5 of those. Okay, so instead of one little formula with only 3 variables in it, we're going to have 5 different formulae with 5 different variables in them to describe constant acceleration. But it's helpful in the back of your head to think of them as kind of one step up from this. So that this is the constant speed or constant velocity situation. Constant acceleration situation requires 5 different formulae, and they're in the second half of this chapter. Now, the second thing is that this chapter, in a lot of ways, you could think of it as 2 sort of mini chapters. Neither of the parts is kind of big enough to make a chapter on its own, so they put them together. And it makes sense because we're dealing with displacement time graphs and velocity time graphs. And on the velocity time graphs, we're going to have a lot of situations where we've either got a constant velocity or a constant acceleration. But section 9.1 and 9.2, in the way that you actually tackle the questions, are largely speaking separate from section 9.3 onwards. What does happen, though, is that you have a section 9.2 question followed, and then part C or D of a section 9.2 question would be something that involves section 9.3 onwards. So you can think of them as 2 separate skills in terms of preparing for the exam. I'd think of the first half up to section 9.2 as one thing, section 9.3 onwards as another thing, and then like often happens in the exam question, they'll mix those 2 skills up. Okay. So you could think of this as 2 mini chapters. So let's crack on with the displacement time graphs then. So first of all, let's have a look at the 3 examples they've got here. If we've got displacement, now I'm going to put my time axis here, so I've got the possibility of a positive displacement and a negative displacement. Okay, so a constant displacement, as time moves, as we move along the x-axis, the displacement on a displacement time graph is the vertical height. So if the vertical height isn't changing, the displacement isn't changing. So a horizontal line is a constant displacement, okay? If you were going along the x-axis or the t-axis, then that would mean you've got a constant displacement and it's kind of at your starting point, whatever you're calling your starting point. Down here is still a constant displacement, so this is still something not moving, okay? So no change in displacement over time. All of these horizontal lines means that you've got no movement happening, all right, wherever the horizontal line is. If it's a horizontal line up here, it just means your position is in the positive position. So if your 0 point was here and this was the positive side and this was the negative side, this horizontal line would be standing still over this side, this horizontal line would be standing still over this side, and a horizontal line along the t-axis would be standing still at the 0 point, okay? So far, so good. Now, if we have if on our t-axis, if we move along the t-axis and we actually do move up and down, so say we've got this sort of situation, what's happening there is as time moves on, your displacement is changing. Now, if you think about that, as time moves on, your displacement changes, then that means you're moving, doesn't it? The number of meters away from the start you are changes per time unit, okay, per second. So that's a certain number of meters per second. So if you've got any sort of vertical change, curved or straight lined on a displacement time graph, that means that you are moving, okay? We know that velocity is, average velocity is displacement from starting point divided by time taken. And if you think about it, velocity is measured in meters per second. And if it's meters per second, well, that's meters is the change in y, seconds is the change in x, isn't it? If we're measuring these in SI units, meters is a vertical distance because displacement is measured in meters. Seconds is a horizontal distance because time is measured in seconds. So meters per second, that's change in y divided by change in x. And the first big idea you've got to get into your head is that the gradient is velocity. On a displacement time graph, gradient is velocity. So for a straight line, the gradient is constant. So if the gradient is constant, the velocity is constant. If you've got something like this, the gradient is changing, so the velocity is changing. Therefore, well, changing velocity, by definition, that's an acceleration, isn't it? So on a displacement time graph, if you've got a horizontal line, it means you're not moving, you're standing still. If the y coordinates are changing at all, then that means there is some movement. If you're going in a straight line, upwards or downwards, you're moving with a constant velocity because gradient is velocity on a displacement time graph. And if you've got a curved line, your gradient is changing because gradient is velocity. That means that a curved line means we're accelerating because by definition, acceleration is a change in velocity, okay? Now, with those things in mind, I think really the questions on this start to become intuitive. What I'd suggest you do is read through the examples. I don't think there's any real need for me to go through them here. You know, I'd be reading out what it says in the book and you can read that for yourself. My advice, though, would be to, and what I'll do in this video, is deal with section 9.1 and 9.2 together and have a look at exercises 9a and 9b together, okay? So you know that 9a is dealing with displacement time graphs because that's part of section 9.1. And you know that 9.2 is dealing with velocity time graphs because it's, because that's what's in there. So 9b is dealing with velocity time graphs. On an exam paper, the difficulty is often identifying which skills you need. So putting those things together, they're identified for you, but dealing with the two exercises as one big exercise is kind of helpful because you're starting to think a little bit more along the lines of identifying which question you've got to do. So the big bullet point so far on displacement time graphs is that on a displacement time graph, gradient is velocity. That is the key thing. If there is nothing else in your notes on this section, in your folder, gradient is velocity on a distant time graph is the first thing you need to put in there. Now on velocity time graphs, so let's do the same thing. Velocity is our y-axis, time is our x-axis. And I'm underlining v there, and I should have underlined the s here because s is a vector quantity and v is a vector quantity. So if I want to show something not moving, well, that means that the velocity has to be 0. Well, the velocity is the y value, so we have to have a y value of 0. And if it's not going to move, then it has to stay at 0 as time moves on. So not moving is this line that I'm drawing now. It's a bit difficult to see because it's also the t-axis, isn't it? So that's it not moving. This line here, now the velocity is the y-coordinate. So the y-coordinate is here. You can say it's 5 or it's 16, I don't know, it's some positive number. Here it's still the same, here it's still the same, here it's still the same. So this is moving and it's moving in the positive direction, okay? If I had a horizontal line down here, then it's moving and it's moving in the negative direction. So this line might be moving that way, this line down here might be moving in that direction. You know, if we've got the usual situation, here's our 0 point and positive is in that direction. So moving forwards, moving backwards. You can think of it like that if you want. And again, velocity is the y-coordinate. If the y-coordinate isn't changing, the velocity isn't changing. If the y-coordinate is 0, the velocity is 0. That's standing still. Okay, so not moving at all, moving with a constant velocity. And then if velocity is changing, well, a change in velocity is called an acceleration. So if the y-coordinate is changing, we have an acceleration. If the y-coordinate is changing in such a way as to give us a straight line, then that means that the gradient is constant, so the acceleration is constant. So on a velocity time graph, acceleration, by definition, that's the change of velocity. So therefore, it's the gradient on a velocity time graph, okay? So this thing here, the gradient is constant, the velocity is changing. We're moving, the velocity is we're moving because we're not just at zero. The velocity is changing, so we are accelerating. The velocity is changing in a way to give us a straight line, so we're accelerating with a constant acceleration. If we've got a curved velocity time graph, then that means we are accelerating, but because the gradient is changing, the amount of acceleration that we've got is changing, okay? On a velocity time graph, if your y coordinates are changing at all, if you're at all moving up and down, then there is an acceleration going on. If it's a straight line, it's a constant acceleration. If it's a curve, it's an acceleration which is also changing. We are going to stick to constant acceleration. It's chapter 9, it's the constant acceleration chapter. So all the graphs we're going to see here are going to be made up of straight line segments. Here we're accelerating, here we're moving at a constant velocity. Here we are, the velocity is going from 8 down to 0. So that means we must be slowing down, okay? So a positive acceleration is a positive gradient here is a positive acceleration, a negative gradient is a negative acceleration. And we talked at the end of chapter 8 about how to deal with positive acceleration when the velocity is positive, and negative acceleration when the velocity is negative, and positive acceleration when the velocity is negative, and negative acceleration when the velocity is negative. So you need to bring in the things from example 5, I think? There we go, example 5 on page 125. These ideas come in handy if you're trying to interpret nasty velocity time graphs like the ones in the challenge question down here. But you'll notice most of the ones in the exercise here, we don't go below the x-axis, so we don't worry about a negative velocity very often, okay? That means if you're just new to this, just deal with the ones like this where the velocity's always positive, and once you're used to those, then maybe take a next step and have a look at the challenge question. So I'm not going to go as far as the challenge question in this video, because this is supposed to be just an overview, getting you up to be able to do these exercises. So, what have we left to say? Acceleration is the rate of change of velocity. So by definition, that's the gradient of your velocity time graph. So I said already, if there's one thing you've got written down, it's that velocity is gradient on a displacement time graph. The second thing that needs to be in your notes, and there are 3 of these really important points, the second thing that absolutely has to be in your notes is acceleration is the gradient on a velocity time graph. And then if we have a look at this example here, if we have a constant velocity, we know that velocity times time is displacement, because we know that speed times time is distance, right? And that just comes from, we know that speed equals distance over time. So distance equals speed times time, okay? So distance equals speed times time. So if I took this velocity, that y vertical distance, the y coordinate there, and I times it by this horizontal distance, this x coordinate, or this t coordinate if you like, I'm getting the area of this rectangle. That's velocity times time. So the area of that rectangle is the displacement, because speed equals distance times time, and velocity and displacement are the vector versions of speed and distance, okay? So that isn't the full argument, but it's just enough to remind you of the last point that's really important, which is the area underneath a velocity time graph is your displacement, okay? I think we're now at the point again where all I'd suggest now in order to get a good handle on this is look through example 2, look through example 3, and make sure those make sense. I could go through it on the video, but I'd just be reading the book to you, so I think you can do that one for yourself, really. The only other thing I'd mention is this. This happens quite a bit. It takes t seconds to get up to a velocity of 8. After 5t seconds, for 5t seconds we move at a constant velocity, then we start braking and decelerating back to a velocity of 0 for 40 seconds. Be careful when you're putting these numbers on the axis. This is a mistake I see quite a bit. So people would have that drawn and they would say that there is t. Well, that's perfectly good. That works with this example. And then they'd say, okay, after 5, we move at constant velocity for 5t. So they would say that this here is 5t. Now that there isn't 5t. 5t is the distance between this point here and this point here. So that there is 5t, that distance. So that makes this t plus 5t. So this is 6t. And this x coordinate here is, or t coordinate strictly speaking, is 6t plus 40, because this gap here is 40. So just be a mistake I've seen a lot is not enough care labeling the horizontal axis. So watch out for that one. Recapping then, if you get these 3 ideas in your head and you have a general understanding of double checking whether it's a velocity time graph or a displacement time graph, then you should be okay. The 3 most important ideas are, if you have a displacement time graph, the gradient is the velocity. There's no important sort of meaning to the area underneath the displacement time graph. If you have a velocity time graph, the gradient is the acceleration, the area underneath it is the displacement. If you've got those 3 things, gradient on a displacement time graph is velocity, gradient on a velocity time graph is acceleration, area underneath a velocity time graph is displacement. If you've got those 3 facts and a general grasp of what's going on, that's all you need for this first half of chapter 9.